in this lesson, we're going to look at another integration method called integration by parts. Integration by parts is based on our formula for finding the derivative of a product. Let's review for just a minute. The derivative with respect to x of two functions u times v. The product rule tells me that this is equal to u times dv dx plus v times du dx. And I could even rewrite that as u v prime plus v u prime. Okay, if both of these functions u and v are differentiable, we can integrate this equation Of course, the integral of this is just uv, and that's equal to the integral of u v prime dx plus the integral of v u prime dx. Okay, if we rearrange a little bit, and the way we usually write the integration by parts equation, we take out the dx part and say u dv and v du. When we want to integrate by parts, we want to make the most complicated part of the integral this dv part. That's just one of our guidelines for figuring out how we're going to split that up. Okay, and then we're going to try to let u be a function that has a derivative that's simpler than u itself. So let's take a look at some examples. We want the integral of x times e to the x dx. Now there's several different ways that we could split this up, but keeping in mind the rule that we want dv to be the most complicated part, it makes the most sense for this part to be dv, which means this part's going to be u. Okay, so if I let dv equal e to the x dx, I know that v is equal to the integral of e to the x dx, which is just e to the x. And if u equals x, then du must be just dx. Now let's write our integration by parts formula. The integral of u dv is equal to u v minus the integral of v du. Okay, let's replace this with what we have. We have the integral of x times e to the x dx is equal to u times v. So it's going to be x e to the x minus the integral e to the x dx. Okay, that's our v du. Okay, and then our final answer would be that this integral is equal to x e to the x minus the integral here is just e to the x plus a constant. Okay, if you'd like to check your work, you can go ahead and take the derivative of this and make sure that you come up with the original problem. Let's do another problem with integration by parts. Let's integrate x squared natural log x dx. Well, the integral of x squared is easier than the integral of natural log x. The derivative of natural log x is simpler than natural log x. So we're going to say that dv is equal to x squared dx, which means that v is going to equal x cubed over 3. And if x squared dx is dv, then u must be natural log of x, and du would be 1 over x dx. So we're going to have the integral of u dv equal to uv minus the integral of v du. Now let's substitute in the things that we know. This is just going to be our beginning statement again. X squared natural log x dx is equal to uv, so natural log x times x cubed over 3 and we're going to subtract the integral x cubed over 3 times 1 over x dx. So now I have x cubed over 3 times the natural log of x minus 1/3. We're taking this 3 out, and then this is going to become x squared. Since this x will cancel out with one of these and make that x squared. So I've got the integral of x squared dx. So now I've got x cubed over 3 natural log x minus 1/3 times the integral of x squared would be x cubed over 3. So when I put these two together, I'm going to get x cubed over 9 plus a constant. And this is my answer. I can use integration by parts even if my integrand only has one part. Let's see how that looks. I've got this integral from 0 to 1, arc sine x dx. In this case, I'm going to let dv equal dx. This means that v will equal the integral of dx, or v equals x. And we're going to let u equal arc sine x, which means that du will equal 1 over 1 minus x squared dx. So now I've got the integral arc sine x dx. So now I can write integral of arc sine x dx is equal to x arc sine x minus the integral. I'm going to take a 1/2 out. I'm going to have 1 minus x squared to the negative 1/2 power times negative 2x dx. So I end up with x arc sine x plus the integral of the square root of 1 minus x squared. And we're going to evaluate from 0 to 1. And when we substitute in, we end up with pi over 2 minus 1, which is approximately equal to 0.571. Sometimes we can use integration by parts more than once on the same problem to get a simpler answer. Let's take a look at that. I've got the integral of x squared sine x dx. And if you look at this, x squared and sine x are both easy to integrate. I wouldn't say that one is any easier than the other, but the derivative of x squared is simpler than x squared. The derivative of sine x is about the same complexity, so we're going to use this x squared as u. So we're going to have u equals x squared, so du would be 2x, and dv is sine x dx, so that v would be negative cosine x. Okay, integrating by parts gives us the integral of x squared sine x dx is equal to negative x squared cosine x plus the integral of 2x cosine x dx. Okay, so this is a little bit simpler than that. But this integral is still not fitting a basic integration rule. So we can take this part and integrate by parts again. So let's write down just this part. Okay, and for this part, I'm going to switch colors so we can kind of keep straight what we're doing. This time we're going to let dv equal cosine x dx. So d is going to equal the integral of that, which is sine x. Okay, then u would equal 2x, and du would equal 2 dx. Okay, now if we integrate this by parts, 2x cosine x dx is equal to u times v, so 2x sine x plus the integral minus the integral to sine x dx, which gives us 2x sine x plus 2 cosine x plus our constant. Okay, now we're going to combine those two results and write it all as one. So here was our original integral, x squared sine x dx equals, we're going to take this part from the first integration by parts, negative x squared cosine x, and then we're going to combine it with this part, plus 2x sine x plus 2 cosine x plus c. Okay, let's look at another one that looks like it's only one part, but we can divide it and make it easier to integrate. We have the integral secant cubed x dx. Now we don't have a rule for secant cubed, but we do have a rule for secant squared. So we're going to divide this up into secant squared x times secant x dx. And we'll let the dv be the secant squared x dx, which tells us that v will be tangent of x. U will be the other secant. So du will be secant x tangent x dx. Okay, so we get the integral of secant cubed x dx is equal to u times v, so tangent x secant x minus the integral secant x tangent squared x dx. You can see that in du we had a tangent x and v was another tangent x. That's why I have tangent squared x. Okay, now I'm going to rewrite that as secant x, and I'm going to rewrite tangent x as secant squared x minus 1. So now let's take what we've got so far. Tangent x secant x minus the integral secant cubed x dx plus the integral of secant x dx. Okay, and it looks like we've kind of gone full circle. We're back to the secant cube, but I'm going to move this piece over here. So now I will have two integrals of secant cubed x dx equals tangent x secant x, and then the integral of secant x is going to be natural log absolute value of secant x plus tangent x. Okay, now to get my final answer, I'm just going to move this 2 over to the other side. Divide everything by 2. So I get my original integral secant cubed x dx equals 1/2 times tangent x secant x plus natural log secant x plus tangent x. And don't forget the constant. Now we're going to go back to an application that we've already studied, finding a centroid, and use integration by parts to work a problem. So I have this region here, and it is bounded by y equals sine x, that's of course the curved part here, and x equals pi over 2 is this right-hand boundary, and of course y equals 0 is the x-axis. So those are our three boundaries. So we want to begin by finding the area of this region. So area is equal to the integral from 0 to pi over 2 sine x dx equal to negative cosine x evaluated from 0 to pi over 2 which would be a value of just 1. So our area is 1. Now we need to find the position of the centroid. Now we're going to use a trig identity to rewrite sine x. Sine squared x is equal to 1 minus cosine 2x divided by 2. now for y bar, I get 1 over a times the integral 0 to pi over 2 sine x over 2 times sine x dx. Okay, remember my area is 1, so this is just 1. So now I'm going to take the 2 out and rewrite this as 1 over 4 times the integral from 0 to pi over 2. Now this is going to be sine squared x, which we just said was 1 minus cosine 2x. And we took this 2 out with this 2, so that's why we have 1/4. And then dx. When we integrate, we get 1/4 times x minus sine of 2x over 2 from 0 to pi over 2. And this gives us a value of pi over 8. I'm going to write that down here. Y bar is equal to pi over 8. And next we'll look for x bar. And now we need to find x bar. So we can write this integral 1 over a times the integral from 0 to pi over 2 x sine x dx. And we're going to let b dv equal sine x dx, and u will be just x, so du is dx, and v is negative cosine x. Okay, now I can use the integration by parts formula. U times v is going to be x, negative x cosine x plus the integral of cosine x dx that would be my v to u. And of course, cosine x dx would be sine x plus a constant going back to my original equation for x bar. From 0 to pi over 2 x sine x dx is equal to negative x cosine x plus sine x evaluated from 0 to pi over 2. And that's also equal to 1. So going back up here, we said y bar was pi over 8. Now we know that x bar is 1. So my final answer should be the centroid is at 1 pi over 8. On page 528, your book has a nice summary of some of the more common integrals for which integral by parts works well. We're going to look at one more instance where integration by parts is helpful, and that's if I have higher powers of something like sine or cosine or e to the x. And this is called the tabular method. So let's say we want to integrate x squared times the sine of 4x. Okay, as usual, we're going to start by letting u equal x squared, which means that du equals 2x. Okay, dv will equal v prime dx, which starts off as sine 4x dx. Now we're going to make a table, and the first column is alternate signs. The second column is u and derivatives, and the third column would be v prime and its derivatives. Okay, and we'll start with a plus sign here. Our original u was x squared, and our original v prime was going to be sine 4x. On our next row, this is going to be negative. Our derivative is 2x. And then we're going to have negative 1/4 cosine 4x. In the next row, we're back to positive. The derivative of 2x is just 2. And here we're going to have negative 1/16 sine 4x. And then our last row, we have negative there. This derivative is now 0. And then 1/64 cosine 4x. Okay? This table is complete. How do I know that it's complete? When I get to 0 in this column, I'm done. Okay, now we're going to make some diagonal lines from the first element in the second column to the second element in the third column, and so on. Like this. Okay, and we're going to multiply these things together to get our derivative. So we're going to start with negative x squared over 4 cosine 4x. And then here I've got a negative, but that's a negative, so this is going to be plus 2/16 would be 1/8. That needs to be an x. So x over 8 sine 4x. And then my last term, I've got 1 over 64 here, a positive 2, so this is going to be plus 1 over 32 cosine 4x. And don't forget the constant. Okay, if you'd like to learn more about the tabular method, your book does have a reference to an article that describes it a little more completely.